The fire that never dies, December 6, 2025. Dawn breaks over the Hawaiian Islands, painting the Pacific in shades of amber and rose. But at Kīlauea summit, another light burns older, fiercer, eternal. A column of incandescent fury climbs toward heaven. Lava fountains erupt from Halema-Umayu crater, reaching heights of 1,200 feet. The molten rock arcs through the pre-dawn darkness like liquid fire hurled from the planet's beating heart. This is episode 38 of an eruption that has redefined our understanding of Earth's restless nature. This is the latest breath of a volcano that has been exhaling fire for 250,000 years. This is Kīlauea, the spewer, the much-spreading, the home of Pele. And this morning, as it has done countless times before, it reminds us that we live on a planet still being born. The fountain tilts southward, driven by winds from the northeast. Hot pumice and molten spatter rain down across the crater rim, destroying a USGS monitoring camera in seconds. Technology vaporized by the same forces that built these islands grain by grain, flow by flow over millions of years. The camera's final images capture its own obliteration. A wall of orange rushing forward, consuming everything. In Volcano Village, 3 miles away, residents step outside to witness the spectacle. Some have seen this show before, many times. Kīlauea has been erupting intermittently since December 23, 2024, each episode more dramatic than the last. But familiarity breeds neither contempt nor complacency here. To live near Kīlauea is to live in conversation with the earth itself, a dialogue written in fire, spoken in thunder, punctuated by the deep seismic breath of tectonic forces beyond human comprehension. The eruptive plume rises 20,000 feet above sea level. Ash, steam, and volcanic gases spiral upward, visible for miles across the Big Island. This is not destruction. This is creation. Every ton of lava that flows from Kīlauea's vents adds to Hawaii's landmass. Every eruption writes another chapter in the longest-running geological story on Earth. This is the world's most active volcano, and we are about to discover why it never truly sleeps. The paradox of paradise. Hawaii. The very name conjures images of tranquility. Pristine beaches, gentle trade winds, the soft strum of ukuleles beneath palm trees swaying in perpetual summer. But beneath this paradise lies violence. The Hawaiian Islands are not ancient, stable landmasses. They are infants in geological time, volcanic mountains rising from the deepest trenches of the Pacific Ocean, born from a wound in the Earth's crust that has been bleeding fire for 70 million years. These islands are temporary, transient. Already, the oldest among them are sinking back into the sea, their volcanic hearts cold, their steep cliffs eroding grain by grain into the waves. But the Big Island, Hawaii itself, is still growing, still rising, still being forged in the crucible of the planet's interior. And at its southeastern edge, where the newest land meets the oldest ocean, Kīlauea stands as both creator and destroyer, builder and demolisher, the embodiment of nature's most fundamental truth. Change is the only constant. Notice the plume rising from Kīlauea's summit, a signature of volcanic activity visible to satellites orbiting 200 miles above. Notice the recent lava flows on its eastern flank, darker than their surroundings, still cooling from eruptions that happened last year, last decade, last century. 90% of Kīlauea's surface is younger than 1,000 years old. 20% is younger than 200 years. This is a volcano that refuses to rest. The statistics are staggering. Since the 1952, Kīlauea has erupted dozens of times. From 1983 to 2018, it erupted nearly continuously for 35 years, one of the longest eruptions ever documented on Earth. During that time, it produced 3.5 cubic kilometers of lava and resurfaced 48 square miles of land. Homes were buried. Communities vanished. The landscape was remade. And now, in 2024 and 2025, it has awakened again. But to understand why Kīlauea behaves as it does, to comprehend the forces that drive its perpetual fury, we must journey backward through time. We must understand not just this volcano, but the very mechanisms that created these islands. We must go back to the beginning. The birth of an archipelago 70 million years ago, the Hawaiian Islands did not exist. The Pacific Ocean stretched unbroken across thousands of miles. But deep beneath the seafloor, perhaps as deep as 1,800 miles beneath the surface, something extraordinary was happening. A column of superheated rock, hotter than the surrounding mantle, had begun its slow ascent toward the crust. This was a mantle plume, a hotspot, a geological blowtorch. As this plume reached the base of the Pacific Plate, the crust above it melted. Magma formed. And that magma, driven by buoyancy and pressure, began to rise through the overlying rock. It punched through the seafloor 20,000 feet below sea level, and it began to build. Eruption after eruption, flow upon flow. A volcano grew in the darkness of the deep ocean, its summit climbing slowly toward the distant sunlight. Decades became centuries. Centuries became millennia, and finally the summit broke the surface. An island was born. But the Pacific Plate was moving. Driven by the grinding forces of mantle convection, the plate traveled northwest at a speed of about 3 inches per year. The island that had formed over the hotspot was carried away from its source. Its volcanic activity ceased. It became dormant, extinct, but the hotspot remained, and so the process repeated. A new volcano formed. A new island rose, and it too was carried away. This is the Hawaiian Emperor Seamount Chain, and it tells a story written in stone. The story of a plate in motion, a hotspot that burns eternal and islands born only to die. Today, the northwestern Hawaiian Islands, Kīlauea, Niihau, are old and eroded. Their rocks are 5.5 million years old. They no longer have active volcanoes. Time and weather have carved deep valleys into their flanks. They are beautiful, but their volcanic fury is spent. Move southeast. Oahu is younger, 3.4 million years old. Maui, younger still, 1.3 million years. Each island represents the hotspot's location at a different moment in geological time. And then, at the southeastern end of the chain, lies the big island of Hawaii. Its oldest rocks are less than 700,000 years old. It has 5 volcanoes. 2 of them, Mauna Loa and Kīlauea, are vigorously active. A third, Waialae, erupted as recently as 1800. And beneath the waves, 20 miles southeast of the Big Island, a new volcano is already forming. Its name is Loihe. Its summit lies 3,000 feet below the surface. In 10,000 years, perhaps 100,000, it will breach the ocean and become the newest Hawaiian island. The process continues. But of all the volcanoes in this chain, past and present, none has been more active than Kīlauea. The shadow of the giant Kīlauea rises on the southeastern slope of Mauna Loa, the most massive mountain on Earth. For years, geologists believed Kīlauea was merely a satellite vent of its colossal neighbor, a parasitic cone feeding from Mauna Loa's deep magma chamber. They were wrong. Kīlauea is its own volcano. It has its own conduit to the mantle, its own magma supply, its own personality. And what a personality it is. Where Mauna Loa erupts with ponderous majesty, its flows broad and slow, its slopes gentle, Kīlauea erupts with wild exuberance. Its summit caldera, Kīlauea, spans 2 miles across. Within that caldera sits Halemaumau, a pit crater that has hosted lava lakes, explosive eruptions, and some of the most dramatic volcanic activity witnessed in modern times. But Kīlauea's reach extends far beyond its summit. 2 rift zones stretch away from the caldera like arms reaching toward the ocean. The southwest rift zone and the east rift zone. These are fractures in the volcano's flank, pathways through which magma can travel miles from the summit before erupting. It is along these rift zones that some of Kīlauea's most destructive eruptions have occurred. The volcano's structure is deceptively simple. It is a shield volcano, so named because its profile resembles a warrior's shield lying on the ground. Unlike the steep, explosive stratovolcanoes like Mount St. Helens or Mount Vesuvius, shield volcanoes are built by countless eruptions of fluid lava. Flow after flow stacks upon previous flows, creating a broad, gently sloping mountain. But do not mistake gentleness of slope for gentleness of temperament. Kīlauea's lava is basaltic, low in silica, high in iron and magnesium. It erupts at temperatures exceeding 2,100 degrees Fahrenheit. When fresh from the vent, it flows like a river of molten glass, racing across the landscape at speeds up to 30 miles per hour. It consumes everything in its path. Forests, homes, highways, farmland. It cannot be stopped, only waited out. And Kīlauea rarely stops. Pele's domain to the Hawaiian people, Kīlauea, is more than a volcano. It is the body of Pele, the goddess of fire, lightning, wind, and volcanoes. Pele is one of the most powerful deities in Hawaiian mythology. She is passionate, creative, jealous, and capricious. Her moods shift like the eruptions themselves, sometimes gentle, sometimes fierce, always commanding respect. To anger Pele is to invite disaster. To honor her is to acknowledge the power of the land itself. Legend tells that Pele fled from her homeland of Tahiti. Pursued by her older sister Nakaoka'i, the goddess of the sea, their rivalry was fierce. Wherever Pele tried to establish a home by digging a fire pit, her sister would follow, using the ocean's waves to extinguish Pele's flames. Pele traveled from island to island across the Hawaiian chain Kauai, Oahu, Molokai, Maui, but each time Namaka drove her away. Finally, Pele reached the Big Island and climbed to the summit of Kīlauea. Here, the volcano's slopes were too high for even Namaka's mighty waves to reach. Pele dug her fire pit in Halemaumau crater, and here she remains to this day. This myth encodes geological truth. The Hawaiian Islands grow progressively younger from northwest to southeast, exactly matching Pele's journey. The oldest islands are eroded, extinct, drowning beneath the waves claimed by Namaka. The youngest island, Hawaii, is still volcanically active, still protected by Pele's fire. Hawaiian oral traditions record Kīlauea's history in chants and stories passed down through generations. One such tradition describes the Kīlauea eruption, a 60-year-long outpouring of lava in the 15th century that covered much of the Puna district. This eruption was so voluminous that it drained Kīlauea's magma chamber, causing the summit to collapse and forming the present-day caldera. Modern geologists, using radiocarbon dating and stratigraphic analysis, have confirmed the essence of these oral traditions. The caldera did form around 1470 CE, a massive eruption did precede it. The ancient Hawaiians witnessed these events and preserved them in their cultural memory. For centuries, Hawaiians have approached Kīlauea with a mixture of reverence and pragmatism. They understood that the volcano could give life, its slopes were fertile, its rocks useful for tools, but it could also take life away. They learned to read the mountain's moods, the earthquakes that preceded eruptions, the glow in the night sky, the smell of sulfur on the wind. They knew that Pele was always watching. The first Europeans on January 20, 1778, British explorer Captain James Cook sighted the Hawaiian Islands. He called them the Sandwich Islands after his patron, the Earl of Sandwich. It was the moment that brought Hawaii into the broader world and the broader world into Hawaii. Cook never visited Kīlauea. He was killed in a skirmish with Hawaiians at Kealakekua Bay on the Big Island's western coast in 1779, but his arrival opened the floodgates. Missionaries, traders, whalers, and adventurers followed. The first European to document a visit to Kīlauea's summit was William Ellis, an English missionary in May 1823. He and 3 companions, including a Hawaiian guide, made the arduous journey from the coast, climbing through dense forests and across barren lava fields. What they found astonished them. Halemaumau crater was a cauldron of molten lava. A lava lake bubbled and surged within the pit, throwing up fountains of fire. The heat was so intense they could barely approach the rim. The sound was deafening, a constant roar like an enormous forge. Ellis wrote of his experience with a mixture of scientific curiosity and religious fervor. He saw the hand of God in the volcano's power. But he also listened to the Hawaiian stories about Pele, about the eruptions of the past, about the dangers that lay ahead. His account marked the beginning of written records of Kīlauea's activity. Before Ellis, we have only oral traditions. After Ellis, we have a continuous documentation of one of the most active volcanoes on Earth, and what that record reveals is both humbling and terrifying. A century of fire. Throughout the 19th century, Kīlauea erupted repeatedly. Some eruptions were gentle lava lakes that rose and fell within Halemaumau, occasionally overflowing the crater rim. Others were more violent, sending lava flows down the volcano's flanks toward the sea. In 1840, an eruption along Kīlauea's East Rift Zone lasted 26 days and produced lava flows that stretched 22 miles. The glow from the eruption was so bright that residents of Hilo, 19 miles away, could read a newspaper by its light at night. In 1868, a magnitude 7.9 earthquake, The largest ever recorded in Hawaii, struck the south flank of Mauna Loa and triggered eruptions at Kīlauea. Landslides buried villages. A tsunami swept the coast. 77 people died. In 1894, lava flows again raced down the East Rift Zone, coming within 2 miles of Hilo before stopping. Each eruption reminded the people of Hawaii that they lived on land still being created, still unstable, still subject to forces they could not control. But perhaps no event in Kīlauea's recorded history has been more dramatic or more tragic than what happened before the arrival of Europeans. In the year 1790, November 1790, the deadliest eruption, the late 1780s, were years of war on the Big Island. Kamehameha, a young chief from the Kohala district, sought to unite all of Hawaii under his rule. But he faced fierce resistance from rival chiefs, particularly Kūākuahuala, who controlled the Ka and Puna districts. In 1790, while Kamehameha was fighting battles on Maui, Kūā raided Kamehameha's lands. When Kamehameha returned to the Big Island, Kūā retreated south to his stronghold. His army warriors, accompanied by their families, women, and children, traveled across the island. Their route took them past Kīlauea. The volcano had been restless for months. Small earthquakes rattled the slopes. Steam rose from fissures. The summit crater glowed at night. Kūā's party made offerings to Pele, hoping to appease the goddess. They set up camp on the western side of the summit, and then Kīlauea erupted. What happened next is recorded in both Hawaiian oral tradition and the accounts of missionaries who heard the stories decades later. The eruption was explosive, far more violent than the gentle lava flows typically associated with Hawaiian volcanoes. A column of ash and steam rose high into the atmosphere, visible as far away as the western coast. Pyroclastic surges, fast-moving avalanches of hot ash, rock, and gas raced across the landscape at hurricane speeds. Kūā divided his party into 3 groups. The first group crossed the eruption zone and survived. The second group, caught in the open when the most powerful surge struck, was annihilated. Warriors, women, children, all perished in seconds, suffocated and burned by the superheated ash. The third group, seeing what had happened, waited. When the eruption subsided, they found the bodies of their companions. Some had been buried in ash. Others lay on the surface, their forms preserved in the positions they had died, some crouching, some running, some shielding their faces from the searing heat. The survivors continued south. Kūā would later meet with Kamehameha to negotiate peace. But at that meeting, Kūā was betrayed and killed, making Kamehameha the undisputed ruler of the Big Island, the first step toward unifying the Hawaiian Islands under a single kingdom. The 1790 eruption killed at least 80 people, possibly as many as 400 or more. It remains the deadliest volcanic event in what is now United States territory. And it left behind evidence that endures to this day. In the Ka Desert, southwest of Kīlauea's summit, you can still see footprints preserved in volcanic ash. Barefoot walkers, men, women, children left their impressions in wet ash during or shortly after the eruption. The ash hardened, preserving the prints. For over 2 centuries, they have remained, a haunting testament to the volcano's lethal power. Modern volcanologists have studied the 1790 eruption in detail. The deposits tell a story of a frito-magmatic event, an eruption caused by the violent interaction of magma with groundwater. When water meets molten rock, it flashes to steam instantaneously. The resulting explosions are devastating, far more powerful than typical effusive eruptions. Such eruptions had been common at Kīlauea before 1790. For 3 centuries from roughly 1500 to 1800, the volcano went through a long period of explosive activity, depositing thick layers of ash across its summit area. But after 1790, the character of Kīlauea's eruptions changed. The caldera floor had risen above the water table. Explosions became rare. Lava flows became the norm. For 200 years, Kīlauea has been in an effusive phase. Lava lakes, rift zone eruptions, long-lived flows that creep across the landscape, spectacular but rarely deadly. But the explosive period will return. Geologists are certain of this. When the summit caldera collapses again, when its floor drops back down to the water table, Kīlauea will once more become a killer. Pyroclastic surges will race across the land. Ash will blanket the summit area. And those who live nearby will face the same dangers that Kīlauea's warriors faced in 1790. The volcano is patient, but it does not forget. Warning signs. The 1790 eruption was not an isolated event. It was part of a long pattern stretching back thousands of years. Geologists have found evidence of explosive eruptions at Kīlauea dating back at least 11,700 years. Some of these eruptions were far larger than 1,790. The Kīlauea ash, a thick deposit of volcanic material near the summit, records explosive eruptions that occurred between 2,000 and 2,700 years ago. These eruptions were massive, spreading ash across much of the Big Island. They would have been visible from space, their plumes reaching into the stratosphere. And they will happen again. Kīlauea is not a dormant volcano waiting to awaken. It is awake. It has been awake for its entire history. The current eruptions, the episodic fountaining of 2024 and 2025, are merely the latest chapter in a story that stretches back 250,000 years. Since December 23, 2024, Kīlauea has erupted intermittently from vents in Haleima-Umaʻu crater. These are not large eruptions by the volcano's standards. They are contained within the summit caldera. Lava fountains reach hundreds of feet into the air, feeding flows that spread across the crater floor. Between eruptions, the summit inflates as magma accumulates beneath the surface. Tiltmeters, instruments that measure tiny changes in the angle of the ground, detect this inflation. Seismometers record the earthquakes that accompany magma movement. Scientists at the Hawaiian Volcano Observatory monitor these signs continuously. They know that another eruption is coming. The question is not if, but when. On December 6, 2025, episode 38, the eruption was particularly dramatic. Lava fountains from the south vent reached heights of over 1,200 feet. The eruptive plume rose 20,000 feet above sea level. Tephra fragments of molten lava cooled into glass rained down across the crater and surrounding areas. Strands of Pele's hair, delicate threads of volcanic glass stretched thin by the wind, were found miles away, draped over trees and fences like golden spider webs. The eruption lasted just over 12 hours. When it ended, the crater floor was covered with fresh lava. 16.5 million cubic yards of molten rock had erupted. 50 to 60% of Haleima-Umaʻu's floor was now new land. And then the volcano paused. But only briefly. Within days, the summit began to inflate again. Tiltmeters recorded the slow upward bulging of the ground. Seismometers detected deep tremors, the sound of magma on the move. Episode 39 is coming. Perhaps in days. Perhaps in weeks. But it is coming because Kīlauea never truly stops. It only rests, and its rests are short. The scientific pivot. Understanding the machine. To understand why Kīlauea erupts so frequently, we must journey deep beneath the volcano's surface. We must understand the machinery of plate tectonics, the physics of magma formation, and the unique circumstances that make Hawaii one of the most volcanically active places on Earth. Imagine, if you will, a vast river of stone flowing through the Earth's mantle. Not liquid stone, not yet, but rock so hot and under such pressure that it behaves like a viscous fluid over geological timescales. This is the mantle, the layer of Earth that lies between the crust and the core. It is nearly 1,800 miles thick. Its temperatures range from 1,400 to 7,000 degrees Fahrenheit. And deep within this layer, beneath the Pacific Ocean, lies a mantle plume. This plume is a column of rock that is hotter than its surroundings, perhaps by several hundred degrees. This temperature difference makes it less dense than the surrounding mantle, causing it to rise. It is slow creeping upward at rates of just a few inches per year, but it is inexorable. It has been rising for millions of years. As the plume ascends, the pressure decreases. And as pressure decreases, the melting point of rock decreases. At depths of about 60 to 90 miles beneath Hawaii, the temperature is hot enough and the pressure low enough that the rock begins to melt. Not completely, only about 10 to 20% of the rock melts. But that is enough. This is magma, molten rock. And once formed, it begins its own ascent toward the surface. Magma is less dense than solid rock. It rises through the mantle and into the overlying Pacific plate, exploiting fractures and weaknesses in the crust. It accumulates in magma chambers, vast underground reservoirs where magma pools, cools, and evolves. These chambers lie several miles beneath Kīlauea's summit. They are not single caverns but complex networks of interconnected pockets and dikes. From these chambers, magma can take several paths to the surface. It can rise directly beneath the summit, erupting into Haleima-Umayu crater. Or it can migrate laterally, traveling through the East Rift Zone or Southwest Rift Zone, sometimes erupting miles from the summit. The magma's composition determines how it erupts. Kīlauea's magma is basaltic rich in iron and magnesium, poor in silica. This makes it relatively fluid when molten. It flows easily. It does not trap gases as readily as more silica-rich magmas. This is why Hawaiian eruptions are typically not explosive. The gases, mostly water vapor, carbon dioxide, and sulfur dioxide, can escape from the magma without building up catastrophic pressure. The eruptions are effusive, producing lava flows rather than ash clouds. But when water is involved, the character changes completely. The explosive exception. When magma encounters water, whether groundwater seeping into the volcanic conduit, or water trapped in the rock itself, the result is explosive. This is a phreatomagmatic eruption. The 1790 eruption was phreatomagmatic. So were many of the eruptions during the 300-year explosive period from 1500 to 1800. During those centuries, Kīlauea's summit caldera was deep enough that its floor lay below the water table. Groundwater seeped into the crater. When magma rose into this water-saturated environment, the results were catastrophic. The Kīlauea tephra, a thick blanket of ash covering much of Kīlauea's summit, dates from this explosive period. In places, it is over 35 feet thick. It records hundreds of eruptions, each one sending ash high into the atmosphere, each one blanketing the land in fine volcanic dust. But around 1800, the explosive eruption stopped. The caldera floor had risen above the water table through the accumulation of countless lava flows. Without water to turn to steam, the eruptions became gentler. Lava lakes formed in Haleima-Umayu. Rift zone eruptions produced long, slow flows. This is the Kīlauea we know today, but it is not permanent. Geologists know that the summit caldera will eventually collapse again. It has done so repeatedly throughout Kīlauea's history. Each time the magma chamber drains, either through a massive rift zone eruption or through a prolonged period of effusive activity, the unsupported rock above the chamber collapses. The caldera floor drops. Sometimes it drops hundreds of feet in a matter of days. When this happens, when the floor drops back to the water table, the explosive period will return. The question is not if, but when. The 2018 cataclysm. A modern warning. To understand what happens when Kīlauea's magma system undergoes a major reorganization, we need look no further than 2018. For 35 years, from January 1983 until April 2018, Kīlauea erupted nearly continuously from Pu'u, a volcanic cone on the East Rift Zone about 12 miles from the summit. Lava flowed from Pu'u down toward the ocean, creating new land, destroying homes, and reshaping the landscape. It was one of the longest eruptions in recorded history. At the summit, a lava lake had been active in Haleima-Umayu crater since 2008. Visitors to Hawaii Volcanoes National Park could stand at the crater rim and watch the molten surface churn and bubble, glowing orange in the darkness, occasionally overflowing onto the crater floor. But beneath the surface, pressure was building. On April 30, 2018, the floor of Pu'u collapsed. The lava lake drained away. Something fundamental had changed in Kīlauea's plumbing system. Magma that had been feeding Pu'u was now moving elsewhere. It was moving downrift, toward the lower East Rift Zone, toward the populated areas of Lower Puna. For the next several days, hundreds of small earthquakes shook the Lower Puna district. The ground cracked. Roads buckled. Residents received evacuation warnings. They had lived with Kīlauea's eruptions for years, but this felt different. On May 3rd, the first fissure opened in Milani Estates, a residential subdivision built on top of the East Rift Zone. Lava erupted onto Mahala Street. Homes were evacuated. Within hours, a second fissure opened nearby, and then a third, a fourth, a fifth. Over the next 3 weeks, 24 fissures opened across Lower Puna. Lava fountains shot hundreds of feet into the air. Flows of a rough, clinkery type of lava crept across yards, through forests, over roads. The flows were viscous at first, moving only short distances from the vents. But on May 4th, a magnitude 6.9 earthquake struck, the largest in Hawaii in 43 years. The quake widened the underground conduit feeding the eruption. Suddenly, magma could flow more freely. The eruption intensified. By mid-May, the character of the eruption had changed completely. Fissure 8, located in the heart of Leilani Estates, became the dominant vent. It produced spectacular lava fountains reaching 200 to 300 feet high. More importantly, it erupted huge volumes of very fluid lava. This was fresh magma, newly arrived from the mantle. It was hotter and more fluid than the older, stored magma that had erupted during the first weeks of the eruption. And it flowed fast. A river of lava poured from Fissure 8, carving a channel through the landscape. It flowed downhill toward the ocean, 7 miles away. It moved at speeds up to 17 miles per hour. Nothing could stop it. Homes were incinerated in seconds as the flow swept through neighborhoods. Trees exploded into flames from the radiant heat. The lava consumed everything: houses, cars, roads, power lines, water mains. By the end of May, the flow had reached the ocean at Kapoho Bay. The entry of lava into the ocean created a phenomenon called laze, a toxic cloud of hydrochloric acid and tiny glass particles formed when molten rock hit seawater. The laze drifted onshore, causing respiratory problems for residents downwind. The ocean boiled where the lava entered, sending up huge clouds of steam. For over 2 months, Fissure 8 maintained this extraordinary output. It erupted an estimated 0.8 cubic kilometers of lava, enough to fill 320,000 Olympic-sized swimming pools. The flow covered 13.7 square miles of land. It destroyed 716 structures, including entire subdivisions: Leilani Estates, Lanipuna Gardens, Kapoho, Vacationland Hawaii, Kapoho beach lots. It also destroyed Hawaii's largest natural freshwater lake, Green Lake, vaporizing it completely within hours. And at the summit, something equally dramatic was happening. As magma drained from beneath Halemaʻumaʻu to feed the Lower Puna eruption, the support beneath the crater floor disappeared. The floor began to collapse. Not slowly, but in sudden, violent events. Starting in mid-May, the summit experienced a series of collapse earthquakes, magnitude 5 events that occurred almost daily. Each one marked another collapse of the crater floor. Each one sent up massive ash plumes. The crater grew larger and deeper with each collapse. By early August, Halemaʻumaʻu had expanded from a crater 280 feet deep to a chasm over 1,600 feet deep. Its volume had increased by a factor of 30. The crater that had hosted a lava lake was now a vast pit, its walls near vertical cliffs, its floor covered in rubble from the collapses. On September 4, 2018, the eruption stopped. Fissure 8 fell silent. The lava channel crusted over. At the summit, the collapses ceased. After 3 months of unrelenting fury, Kīlauea went quiet. But the scars remained. Lower Puna had been transformed. Over 875 acres of new land had been added to the Big Island. The coastline had been redrawn. Communities that had existed for decades were gone, buried under tens of feet of solid rock. The 2018 eruption displaced over 3,000 residents. It caused an estimated $800 million in damage. It was the most destructive volcanic event in Hawaii's modern history. And it offered a stark reminder: living near an active volcano means accepting that the land beneath your feet is temporary. The lava lake returns. After the Archipelago eruption, Kīlauea fell into an unusual state of quiescence. For months, the volcano was nearly silent. Seismicity dropped to low levels. No lava erupted. The summit remained a vast, empty crater. But beneath the surface, magma was accumulating. The hotspot beneath Hawaii does not stop producing magma simply because the volcano above it has ceased erupting. The supply is constant, relentless. In late 2020, seismicity began to increase. Earthquakes clustered beneath the summit, indicating magma movement. Instruments detected inflation. The ground was swelling as magma pushed upward from deep chambers. On December 20, 2020, lava returned to Halemaʻumaʻu. A vent opened on the western wall of the crater. Lava fountains arced into the air, feeding flows that spread across the crater floor. Within days, a lava lake had formed. This new lake was different from the previous one that existed before 2018. The old lake had been small, confined to a pit within Halemaʻumaʻu. The new lake covered much of the crater floor, growing larger with each eruption. By the time the eruption paused in May 2021, the lava lake was over 700 feet deep. Eruptions resumed in September 2021 and continued intermittently through May 2023. Each eruption added more lava to the crater, slowly filling the vast pit created during the 2018 collapse. By mid-2023, Haleima-Umayu contained a lava lake nearly a mile wide and over 780 feet deep, one of the largest active lava lakes on Earth. And then, in June 2023, the eruption stopped. Once again, Kīlauea went quiet. The lava lake crusted over, forming a solid cap over the molten rock beneath. But the crust cracked and buckled as the lava beneath cooled and contracted, releasing gases and occasionally revealing glimpses of orange glow deep within the fissures. For a year and a half, the volcano rested. But it was not dormant, it was recharging. December 23, 2024. The return of fire throughout late 2024, the signs were unmistakable. Seismicity increased beneath Kīlauea's summit. The tiltmeters recorded steady inflation. GPS stations measured the ground rising by several centimeters per month. Sulfur dioxide emissions increased. Scientists at the Hawaiian Volcano Observatory watched these indicators carefully. An eruption was imminent. The only questions were when and where. On December 23, 2024, at approximately 2:20 a.m. local time, the volcano answered. Multiple vents opened simultaneously within Haleima-Umayu crater. Lava fountains burst from the crater floor, brilliant orange against the black sky. Within minutes, lava was spreading across the crater, flowing over the solidified surface of the 2021 to 2023 lava lake. This was episode 1 of what would become a sustained series of eruptions. The fountains reached heights of 300 feet. Tephra fell across the summit area, coating everything in a fine layer of volcanic glass. The eruptive plume rose thousands of feet, visible as a red glow from communities miles away. In Volcano Village, residents stepped outside to watch the familiar spectacle. The eruption lasted 24 hours. When it ended, Haleima-Umayu contained fresh lava covering approximately 25% of the crater floor. The lava was still molten, still glowing, still degassing, and then the volcano paused. For 6 days, Haleima-Umayu was quiet, but scientists knew this was not the end. The summit was deflating slightly. Magma had been released during episode 1, but inflation would resume soon. On December 29th, episode 2 began. Again, lava fountains erupted from vents on the crater floor. Again, lava spread across Haleima-Umayu. This eruption lasted 12 hours and added more fresh lava to the growing lake. A pattern had been established. Eruption. Pause, inflation. Eruption. Pause, inflation. This is how shield volcanoes breathe. Episodic eruptions fed by a steady supply of magma from depth. Each eruption releases pressure, causing a temporary deflation. Then magma accumulates again, the summit inflates, and the cycle repeats. Throughout January, February, March, April, May, June, July, August, September, October, November, and into December 2025, this pattern continued. Some episodes lasted only a few hours. Others continued for days. Some produced lava fountains over 1,000 feet high, taller than the Eiffel Tower. Others were gentler, with fountains barely reaching 100 feet. By December 2025, Kīlauea had experienced 38 eruptive episodes over the course of a year. The crater floor of Haleima-Umayu had been substantially resurfaced with fresh lava. In some areas, the new lava was over 200 feet thick. December 6, 2025, shortly after 4 a.m. on December 6, 2025, seismometers detected a rapid increase in volcanic tremor beneath Kīlauea's summit. Within minutes, the Hawaiian Volcano Observatory issued an eruption notification. Episode 38 had begun. At 4:06 a.m., lava broke the surface within Haleima-Umayu crater. The initial fountaining was vigorous, reaching heights of 500 feet. Multiple vents opened along the southern portion of the crater floor, aligned with the volcano's rift zones. Lava poured from these vents, coalescing into a river that flowed northward across the crater. By dawn, the eruption had intensified. The main vent on the southern side of the crater was producing sustained fountaining reaching heights of 1,200 feet. The fountain was tilted by northeast winds, causing molten spatter to fall primarily on the downwind side. One USGS monitoring camera positioned to observe this vent was destroyed by falling spatter, its final transmission showing a wall of orange, rushing toward the lens before the image went black. The eruptive plume rose 20,000 feet above sea level. Ash, steam, and volcanic gases billowed upward, visible across much of the Big Island. Residents of Hilo reported a strong smell of sulfur. Volcanic fog, a haze composed of sulfur dioxide, water vapor, and carbon dioxide drifted downwind, reducing visibility and air quality in communities south of the volcano. Inside the crater, lava flows spread rapidly. The molten rock was extremely fluid, fresh magma from depth, rich in dissolved gases, erupting at temperatures exceeding 2,100 degrees Fahrenheit. It flowed like water, racing across the crater floor, overtopping previous flows, filling low-lying areas. The sound was overwhelming. Even 3 miles away in Volcano Village, the eruption produced a continuous rumble punctuated by sharp cracks and booms as gas bubbles burst within the fountain. Closer to the crater rim, the noise was physically painful, a roar that shook the ground and vibrated the chest. Photographers and scientists gathered at safe vantage points around the crater rim. The sight was spectacular, lava fountains arcing into the sky, rivers of molten rock glowing orange and yellow, the crater floor pulsing with activity, waves of lava surging from the vent, spreading outward like ripples on a pond made of fire. This is Kīlauea at its most magnificent. This is creation in real time. By late morning, the fountaining had decreased to 600 feet. By early afternoon, it had dropped to 300 feet. By evening, only weak spattering remained. At 4:15 p.m., just over 12 hours after the eruption began, the vents fell silent. But it had been one of the largest episodes to date. An estimated 16.5 million cubic yards of lava had erupted. 50 to 60% of Haleʻauʻu's floor was now covered by fresh lava from this episode alone. The crater floor had risen by several dozen feet in some areas. And already, the cycle was beginning again. Seismometers detected deep tremor magma moving upward from the summit reservoir, refilling the shallow conduits. Tilt meters showed the onset of inflation. In a few days, perhaps a week or two, episode 39 would begin. This is Kīlauea's rhythm. This is how it has behaved for a year. This is how it may behave for years to come, unless something changes. The rift zone threat. While the summit eruptions of 2024 to 2025 have been spectacular, they have also been relatively safe. The lava is confined within Haleʻauʻu crater, inside Hawaii Volcanoes National Park. No communities are threatened. Visitors can observe the eruptions from viewing areas along the crater rim. But Kīlauea's plumbing system extends far beyond the summit. The East Rift Zone and Southwest Rift Zone are pathways through which magma can travel miles from the summit before erupting. And it is along these rift zones that the most destructive eruptions occur. The 1983 to 2018 eruption from Pu'u was a rift zone eruption. So was the 2018 Lower Puna eruption. In both cases, lava erupted far from the summit, flowing through forests and residential areas on its way to the ocean. The East Rift Zone passes directly through populated areas, Leilani Estates, Kalapana, Kapoho, Pahoa. Thousands of people live in subdivisions built on top of old lava flows. They know the risk, but they love the land, the beauty, the connection to Pele's domain. They choose to stay, and Kīlauea will erupt there again. Geologists cannot predict exactly when the next rift zone eruption will occur. It could be years away. It could be decades, but the volcano's history makes it certain. Rift zone eruptions are a fundamental part of how Kīlauea works. When magma accumulates beneath the summit, pressure builds. Eventually, that pressure can force magma laterally into the rift zones. Dikes, vertical sheets of magma intrude into the older rock, sometimes reaching the surface and erupting, sometimes stopping short and solidifying underground. In 2018, the intrusion that fed the Lower Puna eruption traveled 28 miles from the summit before it erupting. It propagated at speeds of up to 1,000 feet per hour, cracking the ground above it, opening fissures in people's yards, erupting lava in a residential neighborhood. It can happen again, and next time it may happen in a different location. The Southwest Rift Zone, though less active than the East Rift Zone, also poses risks. An eruption there could send lava toward the populated areas near Ocean View or toward the coastal communities on the west side of the volcano. Living near Kīlauea means living with uncertainty. The land is precious, the communities close-knit, the connection to nature profound. but the volcano is always there, always active, always capable of remaking the landscape with terrifying speed. The science of prediction. Can we predict Kīlauea as eruptions? To some extent, yes. But prediction is not the same as certainty. The Hawaiian Volcano Observatory, established in 1912 by Dr. Thomas Jagger, is one of the premier volcano observatories in the world. It monitors Kīlauea continuously using an array of instruments that would have seemed like science fiction a century ago. Seismometers detect earthquakes, from tiny tremors imperceptible to humans to large quakes that shake buildings. The pattern of seismicity can reveal magma movement. Swarms of small, shallow earthquakes often precede eruptions. Deep tremor, a continuous, low-frequency signal, indicates magma flowing through conduits. Tilt meters measure changes in the angle of the ground, detecting inflation and deflation of the volcano's summit. When magma accumulates, the ground swells. When magma drains during an eruption, the ground subsides. These changes are tiny, sometimes only microradians, but they are measurable. GPS stations track the absolute position of points on the volcano's surface with millimeter precision. By monitoring how these points move over time, scientists can model the shape and depth of magma chambers, the volume of magma intruding, and the stress building in the volcanic edifice. Gas sensors measure the composition and emission rates of volcanic gases. An increase in sulfur dioxide emissions often precedes an eruption as magma rises toward the surface and degasses. Changes in the ratio of carbon dioxide to sulfur dioxide can indicate whether the magma is coming from shallow or deep sources. Thermal cameras and satellites monitor ground temperatures, detecting hot spots that might indicate magma near the surface. INSA interferometric synthetic aperture. Radar uses satellite radar to measure ground deformation over large areas with centimeter-scale precision. All of this data flows into the Hawaiian Volcano Observatory 24 hours a day, 365 days a year. Scientists analyze the data, looking for patterns, anomalies, and trends. When conditions suggest an eruption is imminent, they issue alerts. In recent years, these alerts have been remarkably accurate. The December 23, 2024 eruption was preceded by several weeks of increasing seismicity and summit inflation. Scientists warned that an eruption was likely. When it began, it surprised no one who had been watching the data. Similarly, each of the subsequent episodes has been preceded by detectable precursors. The pattern is now well established: inflation, seismicity increase, onset of tremor, eruption. The warning time can be as short as a few hours or as long as several days. But not all eruptions follow this pattern. The 2018 Lower Puna eruption, while preceded by signs of unrest, unfolded in ways that surprised even experienced volcanologists. The lateral propagation of the dike, the opening of 24 fissures, the extraordinary output from Fissure 8, these were not precisely predicted. Volcanoes are complex systems. We understand the broad outlines of how they work. But the details, exactly when, where, and how large an eruption will be, remain difficult to forecast with certainty. And there are scenarios that would give little warning. A large earthquake could trigger an eruption within minutes. A catastrophic flank collapse, the sudden failure of a large portion of the volcano's side, could unleash devastating landslides and tsunamis with no precursors detectable by current instruments. So while we can monitor Kīlauea continuously, while we can issue warnings when an eruption is likely, we cannot guarantee safety. The volcano holds some secrets still. The magma beneath. To truly understand Kīlauea, we must go deeper. We must explore the magma chambers that feed the volcano, the complex plumbing system that connects the summit to the rift zones, and the ultimate source of all this activity, the Hawaiian hotspot itself. Beneath Kīlauea's summit lies a shallow magma reservoir approximately 1 mile below the surface. This reservoir is not a single, large cavity, but a complex network of interconnected dikes, sills, and pockets of molten and partially molten rock. It has a volume of several cubic kilometers, enough magma to feed years of eruptions. Below this shallow reservoir, at depths of about 3 to 7 miles, lies a deeper magma storage zone. This zone feeds the shallow reservoir. Magma from the mantle plume rises into this deep storage zone, where it accumulates and evolves. Some of it remains there for decades, slowly cooling and crystallizing. Some of it rises to the shallow reservoir and erupts. The magma evolves as it rises. When it first forms in the mantle, it is a primitive basalt rich in magnesium and iron, with temperatures around 2,200 degrees Fahrenheit. But as it rises and cools, minerals begin to crystallize out of the melt. Olivine forms first, a green mineral rich in magnesium. As olivine crystallizes, it removes magnesium from the melt, changing its composition. This process, called fractional crystallization, causes the magma to evolve toward more iron-rich compositions. The lava that erupts at Kīlauea summit is often more evolved than the magma that feeds lower rift zone eruptions. The 2018 Fissure 8 lava was notably primitive, very hot, very fluid, and rich in magnesium. It had spent little time in storage and had experienced minimal crystallization. The pathways between the summit and the rift zones are also complex. Dikes, vertical or steeply inclined sheets of magma connect the summit reservoir to eruption sites miles away. These dikes are typically only a few feet wide but can extend for miles both horizontally and vertically. When pressure builds in the summit reservoir, magma can be squeezed laterally into these dikes. The dike propagates through the older rock, cracking it open, creating a pathway for more magma to follow. If the dike reaches the surface, an eruption begins. If it stalls before reaching the surface, the magma solidifies underground, forming a new intrusion that adds to the volcano's structure. Geophysicists have used seismic tomography, a technique similar to medical CT scans, to image the interior of Kīlauea. The results reveal complex architecture, zones of partial melt beneath the summit, conduits connecting different depths, and old solidified intrusions crisscrossing the volcano's flanks. And beneath all of this, at depths of 30 to 60 miles, lies the source, the Hawaiian hotspot, a mantle plume that has been active for at least 70 million years and shows no signs of weakening. The hotspot, engine of creation. The Hawaiian hotspot is one of the most powerful volcanic systems on Earth. It has created an entire chain of islands stretching 3,900 miles across the Pacific. It has erupted millions of cubic miles of lava. It has reshaped the ocean floor, built mountains from the abyssal plain to heights exceeding 30,000 feet from base to summit, and continues to add new land to the Hawaiian Islands every day. But what is a hotspot, and why does it exist? The answer lies deep within Earth's mantle. Most volcanism on Earth occurs at plate boundaries, places where tectonic plates diverge, converge, or slide past each other. But hotspots are different. They are intraplate volcanoes occurring in the middle of tectonic plates, far from any boundary. The prevailing theory is that hotspots are fed by mantle plumes, columns of abnormally hot rock rising from the deep mantle, possibly from the boundary between the mantle and the outer core, nearly 1,800 miles beneath the surface. These plumes are thought to be relatively stationary, at least compared to the moving plates above them. As the Pacific plate moves northwest over the Hawaiian hotspot, the plume punches through the plate, creating a volcano. That volcano erupts for hundreds of thousands or even millions of years, building a massive shield volcano. But eventually the plate carries the volcano away from the hotspot. Its magma supply is cut off. It becomes dormant, and a new volcano forms over the hotspot. This process has repeated dozens of times, creating the Hawaiian Emperor Seamount Chain. The oldest seamounts in the chain, near the Eruption Trench, are about 85 million years old. The youngest volcano, Lo'ehi, is still below sea level but actively growing. The hotspot is remarkably consistent in its output. It produces about 0.1 to 0.2 cubic miles of magma per year. This may not sound like much, but over millions of years, it adds up. Mauna Loa, the largest volcano on Earth, has a volume of about 18,000 cubic miles. Nearly all of it erupted from the hotspot over the past 700,000 years. But why does the hotspot exist? What causes these mantle plumes? This is one of the great unsolved questions in geology. Some scientists believe plumes originate from thermal instabilities at the core mantle boundary, where heat from Earth's molten outer core warms the base of the mantle, creating rising blobs of hot rock. Others suggest plumes are generated by chemical differences in the mantle, with pockets of denser or less dense material sinking or rising. Whatever their origin, mantle plumes are powerful engines of volcanic activity. And the Hawaiian hotspot is one of the most active plumes on Earth. Kīlauea's sisters, Kīlauea is not alone. It shares the Big Island with 4 other volcanoes, each at a different stage in its life cycle. Kohala, at the northern tip of the island, is the oldest. It last erupted about 120,000 years ago. Today, it is deeply eroded, its slopes cut by steep valleys. It will never erupt again. Mauna Kea, the highest peak in Hawaii at 13,803 feet above sea level, is dormant. It last erupted about 4,500 years ago. Its summit is crowned with snow in winter and hosts some of the world's most powerful astronomical observatories. But beneath its frozen peak lies an extinct volcanic heart. While Blea, on the west side of the island, last erupted in 1800 to 1801, producing lava flows that reached the ocean and narrowly missed the coastal settlements. It is dormant but not extinct. Geologists believe it will erupt again within the next century. Mauna Loa the giant last erupted in November-December 2022. Its summit towers 13,678 feet above sea level. Its volume is so large that its weight depresses the ocean floor beneath it by 5 miles. Mauna Loa erupts less frequently than Kīlauea, on average, once every 6 years, but its eruptions are often enormous, producing lava flows that can travel dozens of miles in just hours. But what it lacks in size, it makes up for in vigor. Why is Kīlauea so much more active than its neighbors? The answer lies in its position directly over the hotspot. The center of the Hawaiian plume currently lies beneath or very close to Kīlauea's summit. This gives the volcano a direct pipeline to the mantle's magma-generating zone. Magma rises almost continuously, feeding frequent eruptions. Mauna Loa, though still over the hotspot, is slightly offset from the center. Its magma supply, while substantial, is less direct. As the Pacific Plate continues to move, Mauna Loa will gradually be carried away from the hotspot. Its eruptions will become less frequent. Eventually, it will go dormant, like Waubla and Mauna Kea before it. And Kīlauea will follow the same path. In a few 100,000 years, it too will be carried northwest, away from the hotspot. Its eruptions will cease. It will become another dormant volcano in the Hawaiian chain. But by then, Loihe will have emerged from the waves, and the cycle will continue. The human cost for all its scientific fascination, Kīlauea is not merely an object of study. It is home to tens of thousands of people who live on its slopes, farm its fertile soils, and build their lives in the shadow of one of the most active volcanoes on Earth. And periodically, the volcano reminds them of the bargain they have made. The 2018 eruption destroyed 716 structures in Lower Puna. Most were homes, not vacation rentals or investment properties, but the primary residences of families who had lived there for decades. Entire neighborhoods vanished under rivers of lava in a matter of hours. Insurance rarely covered the losses. Most homeowners' insurance policies explicitly exclude damage from lava flows. The risk is too high. The potential loss is too catastrophic. Those who lost their homes in 2018 received some assistance from FEMA and other agencies, but many were left to rebuild on their own or relocate. For some, the loss was financial. For others, it was deeply personal. Homes built by hand over years, gardens planted and tended for decades, family gravesites, all buried under rock. But many of those who lost their homes in 2018 have chosen to stay in Puna. They live in temporary structures on land adjacent to the lava flows. They watch as vegetation slowly reclaims the black rock. They remember the forests that once stood there, the homes that lined the streets, the community that thrived. And they accept that it could happen again. This is the reality of living near Kīlauea. The land is beautiful. The community is strong. The connection to nature is profound. But the volcano is always there, always active, always capable of destruction. Yet there is another side to this story. Kīlauea's eruptions are not merely destructive. They are creative. Every lava flow adds new land to Hawaii. Over the past 40 years, Kīlauea has added nearly 700 acres of new coastline. That land, once it cools and weathers, will become home to pioneering plants, then ferns and grasses, then shrubs and trees. In a century, it will be forested again. The volcanic soils are among the most fertile on Earth. Basaltic lava weathers into soil rich in minerals essential for plant growth. The windward slopes of the Big Island receive abundant rainfall. The combination produces lush rainforests, productive farmland, and an ecosystem of extraordinary diversity. The thermal heat from the volcano also provides resources. Geothermal energy plants tap the heat beneath Kīlauea's slopes, generating electricity for thousands of homes. The Puna geothermal venture, located on the East Rift Zone, survived the 2018 eruption despite being perilously close to the lava flows. So the relationship between Kīlauea and the people who live near it is complex. It is a relationship built on respect, acceptance, and an understanding that the land is not truly owned, it is borrowed, temporarily from forces far greater than ourselves. The global impact. While Kīlauea's recent eruptions have been dramatic, their impact has been largely local. Lava flows have destroyed property and displaced residents, but the volcano has not caused significant global consequences. The eruptions are not large enough, not explosive enough, to inject substantial amounts of ash and gas into the stratosphere. But Kīlauea is capable of much larger eruptions. The 1790 explosive eruption, while deadly, was relatively small in terms of total ejecta. But earlier explosive periods produced far more voluminous ash deposits. The Yucca Kahuna ash and other tephra layers record eruptions that spread ash across much of the Big Island and beyond. If Kīlauea were to experience a major explosive eruption larger than 1790, on the scale of the earlier prehistoric events, the impacts could be far-reaching. Ash would disrupt air travel across the Pacific. Sulfur dioxide emissions could reach the stratosphere, reflecting sunlight and causing temporary global cooling. Local communities would face evacuation, crop failures, and water contamination. Moreover, Kīlauea's position makes it a critical case study for understanding volcanic hazards worldwide. Hawaii is one of the most heavily monitored volcanic systems on Earth. The lessons learned from studying Kīlauea have been applied to other volcanoes in Alaska, the Cascades, Japan, Indonesia, and elsewhere. The 2018 eruption provided new insights into how rift zone intrusions behave, how collapse events at volcanic summits unfold, and how lava flows interact with groundwater and ocean waters. These insights inform hazard assessments and emergency planning for volcanic regions around the world. In a broader sense, Kīlauea reminds us that we live on a dynamic planet. Earth is not a static rock drifting through space. It is a thermally active body, still shedding the heat accumulated during its formation 4.5 billion years ago. That heat drives plate tectonics, builds mountains, and creates volcanoes. And as long as Earth remains thermally active, volcanoes like Kīlauea will continue to erupt. The future of Kīlauea. What does the future hold for Kīlauea? In the short term, the next years to decades, we can expect more of what we have seen in 2024-2025. Episodic summit eruptions will continue. Lava will gradually fill Halema-Umayu crater. Perhaps a sustained lava lake will form, as it did in 2021 to 2023. Eventually, perhaps in the next few decades, the summit reservoir will reach a critical pressure, and magma will intrude into one of the rift zones. A new rift zone eruption will begin, possibly in Lower Puna, possibly elsewhere. Communities may be threatened. Evacuations may be necessary. Lives and property may be lost. Over the longer-term centuries, the summit caldera will eventually collapse again. The floor will drop, perhaps during a particularly large rift zone eruption that drains the magma chamber. The collapse could be sudden and catastrophic, accompanied by large earthquakes and possible tsunamis if landslides reach the ocean. When the floor drops below the water table, explosive eruptions will return. Ash plumes will rise high into the atmosphere. Pyroclastic surges will race across the landscape. The character of Kīlauea's activity will change fundamentally. And over the even longer term, hundreds of thousands of years, Kīlauea will gradually move away from the hotspot. Its eruptions will become less frequent. It will enter a declining phase, like Mauna Loa is beginning to experience. Eventually, it will go dormant, its volcanic fires extinguished, but Earth's fire will not be extinguished. By then, El Oihi will have emerged from the ocean. Perhaps a new volcano will have begun forming even further southeast. The Hawaiian chain will continue to grow, island by island, age by age, as the Pacific plate carries each volcanic child away from its birthplace over the hotspot. This is the pattern that has persisted for 70 million years. This is the pattern that will continue for tens of millions of years to come until the hotspot itself weakens, or until the Pacific plate changes its motion, or until some other geological event reshapes this corner of the Earth. For now, Kīlauea remains vigorously active. The world's most active volcano shows no signs of slowing down. Learning from the fire, every eruption of Kīlauea is an opportunity, not just for scientific study, but for learning how to live with volcanic risk. The knowledge gained from monitoring Kīlauea over the past century has transformed volcanology from a descriptive science into a predictive one. Before the establishment of the Hawaiian Volcano Observatory in 1912, eruptions were unexpected disasters. They struck without warning, catching communities off guard. There was no understanding of the precursory signs, no instruments to detect the subtle signals that precede an eruption. Dr. Thomas Jagger, the founder of HVO, changed that. He believed that by studying volcanoes continuously, by measuring their every twitch and rumble, scientists could learn to anticipate eruptions and provide warnings. He was right. Today, HVO operates one of the most sophisticated volcano monitoring networks in the world. Real-time data flows from dozens of seismometers, tilt meters, GPS stations, gas sensors, and cameras. Satellites provide overhead views of ground deformation and thermal emissions. Drones survey inaccessible areas of active lava flows. This comprehensive monitoring has saved lives. Compare this to the 1790 eruption, which killed scores or hundreds of people who had no way of knowing the volcano was about to erupt explosively.